Welcome to our project presentation, Why Sense Sleep Monitoring Using Wireless Sensing. We are from the group Why Sense. Sleep monitoring is the process of observing a person's sleep patterns and behavior. It helps identify disorders, track sleep stages, and analyze postures. Tools include wearables, sensors, cameras, and even wireless signals like Wi-Fi. Most available tools are either intrusive, expensive, or compromise privacy. Wearables disrupt natural sleep, cameras struggle in low light and raise privacy concerns. Medical-grade equipment is often costly and inaccessible. To overcome these challenges, we built a device-free solution using Wi-Fi signals and channel state information, or CSI, for sleep monitoring in a domestic setting. Our solution uses cost-effective, off-the-shelf hardware. It is non-intrusive and completely privacy-preserving. No need for wearables or cameras, making it ideal for real-world use. Our objectives were to build a CSI data collection system using ESP32 boards, to develop algorithms to extract respiration and heart rate, to detect postures and sleep patterns from these vitals, to design a real-time IoT monitoring system, and to improve accuracy compared to existing solutions. Sleep monitoring methods can be contact-based or non-contact. Non-contact methods include vision, RF, RSS, and CSI-based systems. Our project focuses on the CSI-based approach for its balance of accuracy and privacy. We used two ESP32 boards, one as a transmitter, one as a receiver. Wi-Fi signals reflect off the subject and are altered by physiological movements. The CSI data is collected by the receiver and sent to a Raspberry Pi. A WebSocket connection transfers data to a back-end server which processes and stores it. Finally, the data is visualized on a front-end interface for real-time monitoring. Our data set includes over 60 data points from 15 individuals aged 24 to 27. We collected 6 minutes of presence data, 1 minute for respiration and heart rate, and 4 minutes for posture detection. Ground truth for heart rate was obtained using the Vitals Track belt. Respiration was manually counted. We conducted experiments for 4 tasks: presence detection, posture classification, respiration rate estimation, and heart rate estimation. We used a mix of statistical methods and machine learning models. The goal is to detect if someone is present between the devices. We filter out noise, apply PCA to reduce dimensions, and use a machine learning model to classify presence. For posture classification, we extract 9 features from each signal window. PCA reduces dimensionality, and a model classifies postures into supine, prone, left, or right. In our project, we explored 2 main approaches for estimating respiration and heart rate: a statistical signal processing approach and a machine learning-based approach. For the statistical approach, we designed dedicated pipelines for both vitals. The respiration rate estimation pipeline includes steps like DC offset removal, smoothing, frequency domain segmentation, and subcarrier selection, followed by extracting the peak frequency component to determine the breathing rate. For heart rate estimation, we evaluated 3 methods. The first selects subcarriers based on signal variance. The second uses average power spectral density across subcarriers. And the third adopts a hybrid approach, combining both amplitude and phase information, using heart-to-noise ratio for subcarrier selection. In parallel, we also experimented with machine learning techniques. For respiration rate prediction, we extracted statistical features and used a linear regression model. For heart rate, the process included denoising, frequency domain filtering, dimensionality reduction using PCA, and finally training regression models to estimate the heart rate. This dual-track approach helped us benchmark classical signal processing methods against learning-based models, providing insights into trade-offs between accuracy, interpretability, and generalizability. Now let's take a look at the results we obtained from our experiments and how our system performed across each task. K nearest neighbors gave the best results. We achieved 94.7% accuracy for presence detection and 94% for posture detection. The statistical model for respiration showed a mean absolute error of just 3 breaths per minute. The machine learning model had higher error, likely due to overfitting. Among the statistical methods, the variance-based subcarrier selection gave the best results. In machine learning, our gradient boost model achieved an error of 9.92 BPM. Let's now move on to the discussion, where we reflect on our outcomes and how they align with the project objectives. We achieved nearly all of our objectives, from building the hardware and algorithms to deploying a working system. While we didn't implement sleep stage and apnea detection, we laid the foundation for those in future work. Our biggest challenges included limited access to ground truth devices for respiration, tools that couldn't export data, and difficulty sourcing ESP32 modules that support 5 GHz, which could improve accuracy. Future work includes improving heart rate detection, testing with real sleep subjects, and automating respiration ground truth collection using dedicated sensors. The research and implementation of this project were guided by several foundational studies in wireless sensing, sleep monitoring, and CSI-based vital sign estimation. We would like to acknowledge all referenced work that contributed to the direction and development of this project. In conclusion, our project demonstrates the feasibility of using Wi-Fi CSI for non-contact sleep monitoring. While challenges remain, especially in heart rate estimation, we achieve promising results for presence, posture, and respiration detection. Thank you for your attention.